All right, so we're on lesson 214, a little more AC theory here. We're going to hit impedance and power factor, and then they also get into temporary installations. I think we're going to do just like we did for lesson 213. I'm going to spoil some of the homework problems here, but again, this is a very high-level subject matter. I think for the general student out there, it's just best to be able to sort of complete these equations and these problems and know which equations to use. So that's what we're going to focus on for now, because again, this is a very big and in-depth topic here for certain. So there's, I think, about 5 things I want to hit on. One is going to be impedance of series circuits, total current in a parallel circuit, total current in a series circuit, the phase angle compared to power factor percentage, and true power and apparent power and how they relate to power factor. It's the first time we really get into power factor, true power, apparent power. I think that's kind of an important thing to have a good idea about. And again, just to review there, the RLC is resistive, inductive, and capacitive. So you're going to sort of see those letters and numbers and words fly around here quite a bit. So first one we want to do here, impedance of a series RLC circuit. This should be some review, I hope, but again, everybody's going to do good with some refresher here. So in this problem, the impedance of a series circuit is blank ohms. The circuit has a resistance of 25 ohms, an inductive reactance of 14 ohms, and a capacitive reactance of 10 ohms. And they actually use those values for all these equations we're going to look at, but they use them in different types of circuits, so it changes how we have to approach it. So, right away, the first thing, let's pull some key values out of here that I know we're going to need. The first is that it has 25 ohms of resistance, 14 ohms of inductive reactance, 10 ohms of capacitive reactance. So let's just table those values up there. We'll keep them for now. So next thing you need to ask yourself is, what formula are we using? And if you've already read, or when you do read in the text, you'll find that it is this formula here, right? Z equals R squared plus, in parentheses, XL minus XC squared. So we have Z is our impedance, R is our resistance, XL is our inductive reactance, and XC is capacitive reactance. Again, we saw that in some previous chapters, so hopefully that sounds familiar. So let's go ahead and fill in some values here. We know that R is going to be 25. We know that XL is going to be 14. We know XC is going to be 10. So we'll go ahead and, remembering order of operations here, simplify this. So 25 squared is 625. 14 minus 10 squared is going to be 16. Again, we'll just add those together now, remembering order of operations. And then let's go ahead and find the square root, and we find that our impedance in this series circuit will be 25.318. Okay, and we did that problem first because that'll actually come up. We need to find impedance in another problem coming up here, but that's sort of our first thing we need to tackle here, right? So next up, let's go to this next problem: total current in parallel RLC circuits. So in this case, the total current in a parallel circuit is blank amps. The current is supplied from a 2-pole breaker in a 12208 3-phase panel. The circuit has a resistance of 25, inductive reactance 14, capacitive reactance 10 ohms. Again, they use the same values again. So let's pull out these values that we need. So we need voltage. We didn't have to worry about that on the impedance problem, but we do have to worry about that here. We will need voltage. And the rest of the values are exactly the same. We have our 25 for resistance, we have our 14 for inductive reactance, our 10 for capacitive reactance. Let's go ahead and just keep those values up here. So our formula we need to use here is IT equals the square root of IR squared plus IL minus IC squared. So we have to sort of, what do these things mean here? I is your total amperage, IR is your resistive amperage, IL is your inductive amperage, IC is capacitive amperage. So an issue we have here is, how do we find IR, IL, and IC? Again, should be some review, but let's throw that up here. So IR, our resistive amperage, is going to be ER divided by R. Think of it in Ohm's law, E divided by R equals I. That's really all we're doing here. For our inductive amperage, we have EL divided by XL. Remember, XL is inductive reactance. That's sort of the equivalent of resistance in an inductive circuit. So again, we have E divided by essentially R, right? And then similarly for capacitive, we have IC equals EC divided by XC, or E divided by, again, essentially resistance, or R. But in this case, it's capacitive. So let's go ahead and fill in what we know. We know that the voltage is going to be the same for all these guys. So 208 divided by R, we grab up here is 25. Comes out to 8.32. We can do the same thing. 208 divided by XL, which is 14, our inductive reactance, gives us 14.86. We have IC equals 208 divided by 10, so voltage divided by capacitive reactance tells us 20.8. So that's actually now represents all of these values. So let's go ahead and stick that over there. So now we can start filling in this main equation that we needed to find our parallel current, right? So in this case, now we know that IR equals 8.32. We know IL is 14.86. We know IC is 20.8. Remembering order of operations, we can continue to simplify. 8.32 squared is 69.22. This section here is going to be 35.28, which tells us IT equals the square root of 104.51. Continue that all the way. We get IT equals 10.22 amps. So, again, I really need you guys just to be able to follow the formula. What exactly does each piece of this formula mean? That's where we get pretty high level. I'm not gonna ask you to try to remember that, but we need to know the formula. We need to know how to use it at the very least, right? So moving on, this one's I think going to be a little easier, but similar. We have now total current in a series circuit as opposed to parallel that we just looked at. So total current in a series circuit is blank amps. The circuit is supplied from the 208 volt panel, 25 ohms, 14 ohms, inductive, and 10 ohms capacitive once again. So same exact values. We're using them in a different circuit. So again, let's table those values for later. We're going to need them. So what's our formula for finding current in a series RLC circuit? Well, it is I total equals EA divided by Z, or total amperage equals voltage divided by impedance. So let's take a trip back. How do we find impedance in a circuit? Well, that formula looks like this: R squared plus XL minus XC squared. So let's fill in these values here. 25 squared plus 14 minus 10 squared. Simplify that, we get 625 plus 16. Simplify that again, adding these together, 641. And finally, impedance is 25.318. So we can throw that in there. So now we can actually fill this formula in all together. We know voltage is 208 divided by impedance, which we just found was 25.318. So our total amperage in that circuit would be 8.2. Again, know that formula, sort of know how to follow it, find those values. They all build on each other, as you're seeing by now. So it's important to sort of keep good notes and be able to check back on that. So now let's jump into, they're going to give us the phase angle, and we need to find the power factor based on that phase angle. I'm not going to spend a ton of time on this because in my career I've never worried about a phase angle. Power factor is an important thing. Phase angle to me is not. But for our curriculum here, we need to know how to calculate this. So this problem tells us the phase angle of a circuit is 28 degrees. The power factor is blank %. Well, it's not any big formula to do this. We simply find the cosine of the angle, which is 28 degrees. If you guys took trigonometry in school, you maybe know what cosine means, maybe you don't. Maybe like me, you remembered you did it, but you forget how to do it. Really, you just need to use your calculator to find this. This could be a whole week-long lesson on sine and cosine and everything else. But how do we use a calculator to find the cosine of an angle? Well, hopefully if you got a scientific calculator, you should see a cosine button. If you're using maybe a calculator on your computer like this, you don't see it right away, but it is here. I'll show you how to get that. if we click on this button here, we get this menu, and right now we're on standard. We can click scientific. Notice now we've added this trigonometry button. That's what we're looking for here. So the way we're going to do this is we're going to first type in the angle, which is going to be, of course, 28. Then we're going to click this drop down trigonometry button, or if you're using a regular calculator, you should just see the cosine button there already. But anyway, after you've typed in the angle of 28, go ahead and hit the cosine button, and it tells us we get 0.883, right? So we actually want to find as a percentage, so we can simply go from a number value to a percentage by moving that decimal 2 places to the right. So our power factor percentage is 88.3. Simple as that. So really the calculator does all the work on this one. You guys just need to know cosine is that magic function you're looking for. And then last but not least here, if we have true power and apparent power, how can we find power factor percentage? And as you read the book, whether you haven't read or you're going to, keep in mind, power factor is it kind of represents in non-resistive loads, there's some lost power, right? Or there's wasted power. It goes away as heat and vibration, and it's just not used productively. That's what power factor represents. How much power is actually being used to do what we want versus we're wasting power, right? So most power factors are going to be, say, in the 90 percentage. So if we have 90% power factor, 10% is wasted, only 90% is actually being used. So in this case, we have true power equals 11 kilowatts and apparent power equals 12 kVA. So what's the difference there? First of all, what's the difference between a volt amp and a watt? Hopefully you've heard me say it or heard somebody say it that watts actually take into account power factor. It's volts times amps times power factor, where volt amps is simply volts times amps. In a resistive load, those numbers will always be the same because power factor is 1 for a resistive load. Now we don't have resistive load. We have inductive loads. We have capacitive loads with power factors less than 1. Ideally, you have 1 as a power factor, or 100%, meaning apparent power, true power are the same. On non-resistive loads, your true power will almost always be less than your apparent power. True power will never be more than apparent power. That's super efficiency. If you invent that, you'd be a rich person. But so in this case, we essentially have some lost power. What is that percentage that we are losing? How do we calculate that? We've got a nice formula here. So some values we need to keep. True power is 11 kilowatts. Apparent power is 12 kVA. Our formula is going to be power factor equals true power divided by apparent power. Okay, pretty simple. So we can go ahead and say 11 divided by 12 gives us 0.9167. Now we need a percentage, so again, we can just move that decimal 2 places to the right to give us 91.67. So again, a power factor of 1 or 100% is ideal. That's what happens on a resistive load. On inductive and capacitive loads, we have a power factor less than 1 or less than 100%. Therefore, we have some lost power. True power will always be slightly less than apparent power. The closer they are, the better, but true power is never going to be more than apparent power. The best we can do is have true power equal apparent power. But essentially, in this case, we're losing about 99 or 98.4%. We're only using 98.4% of our power, and